Electricity and electronics have a very special role in today's world. Various types of appliances that we use in our homes work on electricity. Modern appliances used for domestic purposes are operated and controlled electronically. In modern factories, electronically operated devices control and manipulate production. Television and video players are commonly used machines in urban homes. We cannot think about life without the help of electronic devices. Even in remote areas, TVs and radios are common. In our homes, we use telephones for making local and distant calls. Transport systems like railway trains depend upon electronic instruments and signaling devices for correct operation. The weather reports that we read in newspapers and see on television are compiled by various types of electrical and electronic instruments. In modern scientific laboratories, you will see many scientific devices. Computers are amongst the essential items of any laboratory. Instruments used for various measurements use sophisticated apparatus. Precision measurement of scientific parameters is possible with the help of electronic instruments. In a scientific laboratory, you may have seen instruments which display bright, wave-like patterns on a screen. An instrument called the cathode ray oscilloscope is one of the most important instruments ever to be developed. Various types of waveforms that appear on the screen are measured and interpreted by scientific personnel working in the laboratory. Various types of waveforms that appear on the screen are measured and interpreted by scientific personnel working in the laboratory. Detailed investigation and measurement is possible with this instrument. It is a very versatile piece of equipment. The cathode ray oscilloscope can be used to measure potential difference or to show in the form of a graph on a screen how a potential difference varies with time. The cathode ray tube is an important device which led to the development of television, radar, and a wide range of electronic instruments which display electrical signals. In your home TV set, the images that you see on your screen are produced by a cathode ray tube placed inside the cabinet. The heart of every oscilloscope is a cathode ray tube which changes electrical energy into light. Every oscilloscope has a cathode ray tube which we see on the screen in an open form. It has three parts. Number 1, an electron gun for producing a narrow beam of high-speed electrons, which is also known as the cathode ray, in an evacuated glass tube. Number 2, a beam deflection system, which can be electrostatic or magnetic. And number 3, a fluorescent screen at the end of the tube, which emits light where the beam falls on it. The main part of the oscilloscope is the cathode ray tube. The tube has an electron gun, which generates a beam of electrons. The screen at the end of the tube is coated with fluorescent material, so that a bright spot of light is produced where the end of the electron beam strikes it. The brightness of the spot depends on the rate at which the electrons strike the screen. Making the grid less negative makes the spot brighter. To focus the beam and to make a small clear spot on the screen, the potential difference between the two anodes is altered. The two anodes act as an electronic lens. For deflecting the electron beam, two sets of deflecting plates are used. The Y plates deflect the spot vertically, and the X plates deflect it horizontally. A potential difference between the Y plates bends the electron beam. The spot on the screen moves up or down. A straight line is seen because the screen continues to glow for a short length of time after the electron beam has moved on. The length of the trace is a measure of the maximum potential difference. If an alternating potential difference from the mains is applied to the Y plates, the spot moves up and down 50 times a second, making a straight line trace. If the potential difference across the X plates is increased steadily, the spot moves across the screen at a constant speed. This is done by applying a potential difference which increases smoothly and then suddenly decreases. This is called a sawtooth potential difference. On the sweep, the spot moves at a constant speed across the screen to the right, and then the spot moves quickly back to the left of the screen. When a signal is applied to the Y plates, the time base spreads it out along the X-axis, so that the variation of the signal with time can be seen.
An oscilloscope is one of the most important instruments to be used in an electronics laboratory. It's used mainly as a graph plotter, or in other words, whatever voltage that we apply to its input, we can study the variation in this voltage or the waveform of the voltage. Now, it's not only an electrical voltage that we can study with an oscilloscope, non-electrical effects can also be studied with it. Only we have to convert the non-electrical phenomenon into a suitable electric voltage with a transducer. For instance, as I am talking, the sound wave get converted into suitable electric voltage with this microphone, and we can observe the variation in the electrical voltage with this oscilloscope. Similarly, in the field of medical science, the heartbeats of a patient can be converted with a suitable transducer into electrical pulses, which can be observed with an oscilloscope. Now, we shall consider a typical oscilloscope and try to see how we can set it up and make some simple measurements with it. In order to use the oscilloscope, the first thing we do is plug it into the mains and switch the mains power on. Then I switch on the power switch on the oscilloscope, and it takes a little while for the intensity to come up. Then we turn the intensity up so that the beam becomes visible. It may be necessary to adjust the focus control here to get a sharp beam. We can use this position control to move the beam up and down and set it at a convenient location, such as this. Depending on the input voltage expected, we adjust the position of this vertical attenuator to set it at any convenient location. Right now, I've set this at 1 volts per division, which corresponds to 1 volts of electrical voltage per division on the oscilloscope face. This means that each division here corresponds to 1 volts of electrical signal applied at the input terminal. The other important aspect that we need to consider is the horizontal scale or the time scale. I can adjust the position of the beam with this control so as to make it start at a convenient location such as this. Then I can also adjust the amount of time per division on the time scale. For this purpose, we use this knob, which is for the time-based control. We can set its position conveniently so as to get an appropriate value of times per division on the oscilloscope phase. Right now, I'm setting it at 1 millisecond per division. This is the input connector where we apply the input voltage to be monitored on the oscilloscope. We use this probe which has a connector which goes into this input terminal like this. Then we use this probe tip to probe whatever voltage we want to measure. Now, I have here for illustration, here is a power supply which is giving out DC voltages at several values, and we would want to measure one of them, typically this. So I connect the probe to this terminal and the beam shifts to its new position here, which is shifted from the original position by 1, 2, 3, 4 and 5 volts. So the voltage that I am applying here is measured to be 5 volts. In order to illustrate a typical AC voltage measurement, we have used this audio signal generator, which can give out a convenient audio frequency with these knobs and a suitable voltage with these knobs. The outputs are available in the sinusoidal form on these terminals or in the square form on these two terminals. We connect the probe to the sinusoidal output terminal of this audio signal generator, and the sine wave appears on the oscilloscope phase here. We observe that this wave has an amplitude of 1, 2, 3, 4, 5 and 6 volts from peak to peak, which is the amplitude of the waveform that we are giving from the audio signal generator. We can also measure the frequency of this signal. We observe that one complete wave from here to here has one complete division of the oscilloscope phase, which corresponds to 1 millisecond, which is the period of this waveform. In other words, the frequency of this wave is 1 kilohertz. Now we illustrate another waveform, which is a square waveform, which is also available as an output from this audio generator. I switch from sine to square, and I put the probe from the sinusoidal output terminals to the square output terminals here, and this is the output square waveform which is visible on the oscilloscope phase.
You should study the function of the controls of the cathode ray oscilloscope, or CRO, thoroughly before you start conducting experiments with it. The focus. This controls the potential difference between the two anodes. Brightness. This makes the grid more or less negative. XY shift. This varies the number of volts across the deflecting plates, so that the spot can be zeroed on the center of the screen. Time-based switch. This alters the length of the time. The spot takes time to move across the screen. Amplifier. This magnifies the signal on the Y plates so that a small potential difference makes the spot move a large distance. When you are performing experiments with the CRO, you should note some practical points carefully and observe certain precautions. The brightness or intensity control, which is usually the on-off switch as well, should be as low as possible. When there is a spot on the screen burn occurs and the phosphor may be damaged. If possible, it is best to defocus the spot or draw it into a line running the time base. When preparing the CRO for use, set the brilliance, focus, X-Y shift control to their mid positions. The time base and Y amplifier gain controls can then be adjusted to suit the input. Two frequencies can be compared from the figures appearing on the screen of the CRO.
Sir, what are the precautions needed when we are operating a CRO?
First is that we must check the power supply. Here we are giving the power supply single phase, that is 230 volts, and 50 Hz main supply, that is the domestic supply. So we have to apply that much voltage to give the power to this one. And that socket must be arched such that there is no shock hazard on this CRO, because this body and all these terminals are being arched, so there must be arch terminal on the socket.
So why do we use this CRO instead of various other instruments like voltmeter?
The difference, the voltmeter is this VTM or any galvanometer type voltmeter, that when we are measuring the AC signal, then in that case AC signal is converted into the DC signal, and then that is calibrated in terms of the RMS values. And in this case here, this is the advantage, we can display the signal, so we can measure the peak to peak value. So there are less chances of error, or you can say this is more accurate instrument for the measurement of peak to peak voltage of the CRO.
Sir, what is peak to peak value?
If you see the waveform, then if you measure the vertical distance between the positive maximum point and the negative maximum point, this will be the peak to peak value of the voltage. Now if you divide by the factor of 2, then it will be the maximum value of the signal.
So what do you mean by RMS voltage?
In this varying signal, the voltage is varying with respect to time. So RMS value is the root mean square value of the signal. So in this case, if you know the maximum value of the voltage, that is Vm, peak voltage, then you can find out the RMS value by dividing a factor of 1 by root 2 to the Vm.
We have seen in this film the functions of a cathode ray oscilloscope and its use. The CRO is used mainly to display the waveform applied to its input. The heart of the CRO is the cathode ray tube. The cathode ray tube changes electrical energy into light signals. The cathode ray oscilloscope can be used to measure voltage. The CRO can display waveforms. The frequency of the waveform can be found by using a CRO. The CRO can be used to compare two frequencies. The CRO is an essential instrument in any scientific laboratory.